Molecular shape and polarity. We've talked about polar bonds. If we have a simple molecule, a diatomic molecule like hydrogen chloride, where we just have two atoms, if the bond is polar, then the whole molecule is going to be polar. Here, hydrogen and chlorine do not share their pair of electrons equally. Chlorine hogs the electrons or is more attractive to the electrons, and so this end of the molecule has a slightly negative charge. It has a larger electron density, higher electron density. This has a low electron density. The molecule itself, being polar, affects the chemical and physical characteristics of that substance. What about the polyatomic molecules? Well, the polarity of the molecule is going to depend on the geometry. If the dipole moments of individual bonds cancel each other out, then the molecule will be nonpolar. If they don't cancel each other out, the molecule will be polar. And so we have to know geometry before we can look at whether a molecule is polar or not. Let's look at carbon dioxide. Carbon dioxide has two polar carbon-oxygen double bonds. Here's the shape of it down here. We've talked about this one before. There are two groups, and so they're on opposite sides. So we have the oxygen pulling the electron density away from the carbon in this direction, and the other oxygen is pulling electron density away from the carbon in the opposite direction. This is like two people playing tug-of-war, and here's the flag in the middle of the rope. They're pulling in opposite directions, equal strength. Is anything going to move? No, they're just going to stand there pulling on the rope. Nothing's going to happen. That's a nonpolar molecule. When we look at the electron density of the oxygens is a little greater than at the carbon in the center, but we don't have one end of the molecule that's different than another. And so there are no poles. There's no dipole moment for the entire molecule. Carbon dioxide is one of the simpler ones to think about because it's two-dimensional and we can visualize it very easily. What about when things get more complicated? Well, dipole moments are actually vector quantities. I don't know if you remember that from math class. Vectors have a direction and a magnitude. The direction is easy to identify. The vector is going to point to the more electronegative element because that is more attractive to the electrons. The magnitude will be proportional to the difference in electronegativity. If we have a small electronegativity difference, the magnitude of the vector is small. If we have a large electronegativity, the magnitude of the vector is small as well. So let's look at water. Water has polar oxygen-hydrogen bonds. And when we draw the Lewis structure for water, let's put it over here, we often draw it like this. And if we don't think about geometry, we might say, well, this bond is going in this direction. This direction, no, this direction. And this bond is going in that direction. They're pushing on each other and nothing's going to happen. But that's not the actual shape of the molecule. That's how we draw the Lewis structure, but that's not the shape. It's actually bent because of these lone pairs pushing these bonds closer together. And so we have one dipole coming up this way and another coming up that way. And they're not going to cancel each other out like they did in the carbon dioxide. And so we have a net dipole in this direction. Yeah, there, it's dashed here. So this is the net dipole. This is from adding these two vectors. And if you think about tug-of-war, here you've got one really strong person, maybe big brother, and two little brothers, and he's playing tug-of-war with both of them at the same time. And they're pulling, this one's pulling this way and that one's pulling this way, but this one's stronger. So what's going to happen to the whole group of them? The strong guy is going to pull both of them backwards, right? That's the movement, that's the dipole moment. And so this end of the molecule is more negative and this end is more positive. Does that make sense? This is kind of an abstract concept, and so I'm trying to make it a little more concrete. So here's a set of instructions of what to do, figure out if it's polar or not. First thing is you've got to draw the Lewis structure and figure out the molecular geometry. Then identify if the molecule contains polar bonds. Just as a rule of thumb, if the two elements are different, they're most likely a polar bond. If they're the same, they are definitely a non-polar bond. On some of the homework, you may have to actually look at the table of electronegativities and figure out, well, does that constitute a polar or non-polar bond? So identify any polar bonds, indicate those with vectors pointing toward the more electronegative atom. Determine if the polar bonds add together. If those vectors add to 0, it's nonpolar. If they do not add to 0, then the molecule is polar. So let's look at vector addition. In one dimension, the vectors lie on the same line. So decide which direction you're calling positive, and then add the vectors together. So if we have two vectors going in the same direction, and they each have a magnitude of 5, when we add these together, we're going to have a vector that has a magnitude of 10. If we have vectors going in opposite directions, and one is a 5 in magnitude and one is a 10, because they're going in opposite directions, one's negative, one's positive, but they're still going to add up to a net vector of plus 5. In this example, we have the same magnitude in opposite directions, and those are going to add up to 0. Does that make sense? It's going to get a little more complicated with each slide, so I don't want to lose you yet. Everybody okay with that? When you have two or more dimensions, one way to add the vectors is to draw a parallelogram with those two vectors forming two adjacent sides. So if we're adding here A and B, we're going to use those vectors as two sides of the parallelogram. And then this side is going to be parallel to B, and this side is parallel to A. So that's this step here. And then the vector sum is starting from the origin where those two were and going to the point of the other one. In this example, here's A and B. We draw the parallelogram, and the sum goes diagonally across. You could figure out its length if you want to, but we don't want to. If you're adding 3 or more, just deal with 2 at a time. Add 2 of them first, and then take that sum and add the third one. If you have another, then add that as well. So here we've got A, B, and C. So first we're going to add A and B, and we're going to get this guy right here. That's R. Now we're going to add R to C. We draw the parallelogram, and this is R prime. And so from these 3, the net vector is to the right. In this example, we have A, B, and C. This would form a triangle, an equilateral triangle with all the sides all the same, because A, B, and C here are the same in magnitude. So when we add A to B, we get R, and when we add R to C, we get 0. Everybody okay with that? So common situations that happen with molecules. If you have a linear molecule and the two, my pointer is just not working very well. If the magnitudes of these are the same, that's going to add to 0. If you have a bent molecule, if the bonds are polar, the molecule's going to be polar. If you have trigonal planar and the magnitude of each of these vectors is the same, that's going to add to 0. If you have a tetrahedron and the magnitudes are the same, that's going to add to 0. If you have a trigonal pyramid with the same magnitudes, it's going to have a net dipole, and it'll be a polar molecule. So in this illustration, when the dipoles of 2 or more polar bonds are canceling, we're assuming that the bonds are identical, like a carbon-oxygen or a phosphorus-hydrogen or something like that. I don't think I have that in here. I'm gonna give you my my shortcut. So adding vectors is the rigorous way. I would encourage you to try to figure that out, to at least understand the idea of it. But I'm going to give you a hack that works most of the time. Looking at a central atom, that will be nonpolar if both of these things are true. If there are no lone pairs, and if the, let's just put it this way, electronegativities are the same. So what does that mean? Well, if you have something like methane, here's the Lewis structure. If I look at that central atom, I see there are no lone pairs. And I see that all the atoms bonded to the central atom are the same. The electronegativities of all of these atoms are the same. That means the magnitude of the dipole on each of these 4 bonds is the same because the electronegativity difference is the same. So that's a nonpolar molecule because those vectors will cancel out. If I switch out one of these and make it chlorine, is the electronegativity of chlorine the same as hydrogen? No. I'm like, oh, I don't have a table to look it up. Well, your best guess is, since they're different elements, that no, they're not the same. So in this situation, the magnitude of the carbon-chlorine dipole is different than the carbon-hydrogen dipoles. So even though the angles are right, one of them is larger than the others or smaller, and so this one's going to be polar. For it to be nonpolar, both of these things have to be true. You notice the tetrahedral is the shape we get with no lone pairs. And trigonal planar is a shape we get with no lone pairs. This one, trigonal pyramid, requires lone pairs, doesn't it? Something like ammonia. Ammonia has 4 groups, but only 3 actual bonds. So one of them is invisible. That's what gives us this trigonal pyramid shape. This lone pair makes the molecule lopsided and therefore polar. Bent is another structure that you can only get if you've got lone pairs. And so the presence of a lone pair should be a big clue. This is going to be polar. So let's do a couple of examples. Determine if CF4 is polar. Well, we got to do the Lewis structure. I'm going to assume that you guys are pretty okay with that, and so I'm just going to draw it out here and not really talk about it too much. Come on. So here's my Lewis structure for carbon tetrafluoride. So from my polarity hack, is that going to be polar or nonpolar? Does it have lone pairs on the central atom? No. Are all the atoms bonded to the central atom the same? Do they have the same electronegativities? Yeah. So no lone pairs, electronegativity is the same. It must be nonpolar. This one is nonpolar. So let's look at how that is. Well, if we draw this guy, it's going to have what shape? Tetrahedron. So we have these 4 bonds going in opposite directions, spread out equally in 3-dimensional space. All the vectors are the same length. And so they're going to add up to 0. You could draw all the parallelograms if you want to, but personally I don't want to. Any questions? Polarity has a big effect on properties of substances. Water is a polar molecule. It has a negative end and a positive end. And there is attraction between the partial positive charge of one and the partial negative of another, just like there's attraction between opposite poles of a magnet. And so water molecules tend to stick together more than nonpolar molecules would. So if we have a collection of marbles, and here we have magnetic marbles, those are the solid colored ones, and these glass ones are not magnetic. These marbles don't stick to each other, but the magnetic ones do. If you dump all of these in a bucket and shake it up, what's going to happen to all those magnetic marbles? They're going to just all clump together, aren't they? And the glass marbles are not going to be included in the clump of magnetic marbles. They're going to be excluded. And this is what happens with things like oil and water. The water molecules are like the magnetic marbles. They're attracted to each other. They're going to kind of stick to each other. Oil molecules are nonpolar. They don't have that attraction. They don't have the attraction for each other. They don't have the attraction for the water. So the water's sticking together and the oil gets pushed out. You make some Italian salad dressing and you shake it all up, right? And you set the bottle down and you watch it, and little globules of oil float to the surface, and pretty soon you've got the oil and vinegar on the bottom. I'm sorry, the water and vinegar on the bottom and the oil on the top. Because the water molecules are sticking together and they're pushing out the oil. If you get oil on your hands or grease or Crisco or something, you can't just rinse it off with water. It's just not going to come off, right? We've probably all had that experience. You get all buttery fingers and you can't just rinse it off. You need some soap. How does soap work? Well, here's an illustration of a soap molecule. A soap molecule has a polar head. Here we've got carbons and oxygens. It's got this head that's polar, but this long tail that's nonpolar. So this polar head is attracted to the water molecules. It'll stick to the water molecules, but this part's going to not stick to the water molecules. This is going to interact very nicely with the grease or the oil, though. And so what happens is the soap actually forms micelles with the oil. So let's say we've got this little glob of grease, okay? and outside we've got the water, and we're trying to get this grease off of our hands. Well, the soap molecules, here's the little head of the soap molecule, and here's the tail. The tail is going to interact with the grease. And so the soap molecules are actually going to surround little bits of grease and oil and form what's called a micelle. Michelle without the H. And now this is almost like it's wearing a costume for Halloween. It's disguised as something that's polar. The outside of this micelle is polar and will be attracted to the water. And so it can move in among the water and get washed away. And the grease in here is being held inside of all these little nonpolar tails. So that's how soap works.